Hello dear students, welcome to the lecture series on VLSI lab. This is VLSI lab from part B, lab number 6B, and in this lab we are going to perform the layout operation on the experiment what we have done in the previous lab of CMOS inverter schematics. Okay. Now, in the previous lab we have done the schematic of inverter as you can see on screen. Now, in this lab we are going to perform the layout operations on the same schematic that we have performed in the previous lab. So, basically we are going to understand how to draw the layout starting with a simple inverter. Now, in the previous lab we did one analysis on the schematic, that is the transient analysis, and there was one more analysis that was supposed to be done, which we called as an DC analysis. Now, what we are going to do is the DC analysis we will be doing it in on the layout that we are going to draw in this lab. So, basically on the layout whatever I am going to draw, I will be telling you how to perform the transient analysis as well as the DC analysis. Now, before heading into what exactly the layout operations or how exactly I should be drawing the layout, the first and foremost thing that as an engineer we should understand is how to start drawing the layout. And to start drawing the layout, one should understand clearly how to draw the stick diagram. And to draw this stick diagram, it is very mandatory to understand how exactly the circuit looks. So, in this lab we are going to understand how exactly one can draw the circuit, and from that circuit how can one can convert the circuit into stick diagram, and from stick diagram into layout, and after that we are going to draw the layout on the electric tool, and we are going to perform the transient as well as DC analysis. So, that is what we are going to perform in this today's lab. So, let us start with the stick diagram of this inverter. So, what I am going to do is I am going to open up a paint over here, and then that would be easy for me to draw all the schematic and the other options of your layout. Fine. So, let us consider, I will just copy paste the inverter schematic over here, and for time being I will also copy paste the NAND gate schematic also. So, what I will do, I will just copy the NAND gate schematic what we have drawn in the previous, basically in my laboratory work I have this NAND gate option also. So, what I will do, I will take this NAND gate also just for the reference, so that we can learn by comparing the things. It will be easy for us to do those things. Yeah, fine. So, here is my inverter and here is my NAND gate. So, I will start drawing the stick diagram with respect to this inverter circuit first, and then we will look into this NAND gate, and parallelly we will be able to achieve both the stick diagrams for the inverter as well as the NAND gate. Fine. So, the first rule that I need to understand, I presume that all the students are knowing how to draw the schematic of the different gates. I am not going to get into that aspect, but what I am going to show you how to convert a given stick diagram into given circuit into a stick diagram through Euler's graph. So, Euler's graph is a very simple way to draw. Now, just look into the number of transistors. So, I have two transistors over here, and I am just going to draw. A figure like this. So, what exactly this means? So, this is one path which is covering from VDD to out. So, here is my VDD V node and here is my out node, and this is one more path covered by this transistor from out to ground. Yes. And for both these transistors the input is IN. Now, for time being I am going to assume the input as A, is not it? For this transistor as well as this transistor the input is A. Fine. Now, the rule says look at that path that each transistor traverses, touching all the nodes and not repeating the paths. Pretty confusing, but let me make it very clear. So, the agenda here is to traverse from one end to another end, once for PMOS and once for NMOS, in a such a manner that all these nodes means these points, all these points should be covered. These points can be covered multiple times, it can be touched, but the path, the way, if I traverse this way, let us say if I have something like this. Now, if I travel once over this path, then again I cannot travel back over here, but what I can do, I can travel like this, this. If I do this, I am reaching here once again. See, earlier I reached from here to here, and while traveling down, and once I come over here, again I reach over here. So, that is acceptable. The no points can be reached again and again, but the path cannot be traced more than once. Now, here obviously there is a single path A. So, what I am going to write is, I am going to write A. So, A is my single path, and that I am going to write it over here, and to the A only I am going to give the input. So, this is my A, and to travel or to traverse path A, what are the points that are covered? The points that are covered are V, O or OV. So, I am going to consider it as something like, so what I will do is, I am going to write it as A, so to traverse A, in the PMOS I cover VO, and in the NMOS also I can go from O to G or G to O. So, preferably I am going to write G to O, because I want to ensure O and O come on the same side, just to have the synchronous kind of thing, fine. And then I am going to draw one horizontal line like this, as well as like this, and one more bigger line like this. So, that I am going to show it with the gray color, and here also one more bigger line like this. So, this is your VDD and this is your ground. Now, the only thing now we are supposed to do is connect the common points to each other. So, what are the common points? Now, I have O and O being common points, I am going to join it, and this will be my output. And V and VDD are common. So, wherever V is there, I join it to VDD, and wherever G is there, I join it to ground. That is it. This is how I am going to draw the stick diagram of this inverter. Now, what exactly this color coding mean? Now, always remember, when we had this cross sectional view of the MOSFET, there is a channel being formed, and on top of that there is an oxide, and on top of that there will be metal, right. So, this oxide is represented, or it is a pure form of oxide, which we also call it as polysilicon, and in the layout always the polysilicon are represented with a red color line, and metals are always represented with a blue color line, specifically metal 1. And other combinations or other color coding I am going to show it during the simulation only. So, these two things you are supposed to remember. Polysilicon is always represented with a red color and metal with a blue color, and the input is always given to oxide through the help of metal. Remember, on top of oxide there is a metal, and you are giving the input to the metal, and where exactly the metal is connected to the polysilicon. So, that is the reason you are giving to the gate. Look here, to the gate only we are giving the input, right. So, and what exactly the gate is made up of? The gate is made up of polysilicon. So, we are giving the input to the polysilicon, hence this polysilicon I am going to mention it as a input A, and this has resulted into this schematic. So, this is how exactly I am going to represent the context of a stick diagram with respect to this inverter. Now, the same stick diagram I am going to convert it in the form of a layout. Once we are done with this, we are going to coming back to this particular NAND gate, and then we are going to perform the similar NAND gate layout as well. Now, what I can do is I can just have yes. Now, can we do similar exercise with respect to NAND gate? Let us try to do it. So, first we are supposed to draw the graph. The graph should look the way how the schematic is drawn, and the curves represent the number of transistors that are present in the graph. Now, there is one transistor present over here from VDD to out. So, one curve, name it as V, sorry, O. These names you can give it anyway as per your wish, but here I am giving just to identify the nodes with respect to those terminals. And there is one more transistor again between VDD to out. So, there is one more transistor. Now, this transistor is given the input A, look here. So, I mention it as A, and this is given the input B, I mention it as B. Now, from out to intermediate point there is one transistor. From out to intermediate point, let me call it as intermediate point as X, there is one transistor, and again from one more intermediate point till the ground there is one more transistor. So, rather than this I can also draw this way also, and this is ground, and this transistor happens to have the input A. So, I am going to mention it as A, and this transistor happens to have the input B. I am going to mention it as B. Done. So, this is your Euler graph. I am going to mention it as O once again. So, this is my Euler graph. Fine. Now, based on the Euler graph, I am going to draw the layout, but before layout I am going to draw the stick diagram. So, what are the stick diagram funda that I have shown? The first and foremost thing, I am going to represent one horizontal line which I am going to say it as VDD, and the next horizontal line which I am going to call it as ground. And next immediately I am going to draw two vertical lines which will be my polysilicon, or which are the points where you are going to be the inputs. And here you have two inputs, one is A and one is B. Although A is given to both PMOS and NMOS at the same point of time, as you can see over here in the circuit, A is given at the same point of time to both PMOS and NMOS, and B is also given at the same point of time to both PMOS and NMOS. So, altogether I have two input NAND gate. So, my two inputs will be something go like this. So, those two inputs are your polysilicon, and do not cross these polysilicon through this VDD and ground. Yeah. Now, whether this is A or this is B or this is B or this is A, it depends on the path what I am going to choose. So, let us say, so I want to choose a path. So, the rule is choose a path wherein all the, or choose a graph wherein all the paths are traversed touching all the nodes, and no path is traversed more than once, and the same path should exist in the NMOS side also. Like for example, here if I say from this path A and B, just check below whether the same path exists. Yes, A, B. So, which means I can name this as A, B, and since this is A, this also will be A because it is the same polysilicon, and the same input is given to both PMOS and NMOS at the same time. So, which means if I call it as A, this is also A, and it is quite visible over here. Now, in order to travel from A to B, what are the nodes that are traversed? I started with V, which means V, O, V. So, write it from the leftmost side, V, O, V. And what are the paths, or what are the nodes that are covered by traversing A and B? O, X, G. So, O, X, G. And the next step is to have two more horizontal lines which will be your N well and P well, and connect the similar points to each other. Now, where do I have similar points? O and O is here is there. So, I am going to connect O with O, and that will make my output. So, this is my output, and X, there is nowhere X related and it is a common point which is over here, leave it as it is. G should be connected to ground, V should be again connected to VDD, and this V should also be connected to VDD. That is it. So, this comes over your, this becomes your stick diagram of your NAND gate. Now, I can also have path represented as BA. Under that scenario, this becomes B, this becomes A, and all the nodes will begin V, O, V I can have this way, or O, V, O I can have this way. So, any path you can choose until and unless it satisfies the rule. So, this is all about your NAND gate, and I request everyone to convert this stick diagram of the NAND gate into the layout, but before we will start working on the layout of the inverter. So, this is the inverter layout, I mean stick diagram. So, let us try to convert that stick diagram of our inverter to the layout. So, here I am going to create a new cell, I am going to call it as INV layout, and then I am going to choose layout. Okay. The procedure all will remain same, and the components are converted as per the layout. So, fine. So, what is that I am going to have now? As we discussed here, I am going to close it now. Yeah. So, I should have this is one VDD and one ground. So, before that let us try to get something called as, let us try to build the transistor. So, here you can see PMOS. So, click on the PMOS, place it over here, and this red patch what you can see, this is your polysilicon. Now, since it is horizontally placed and here I need the vertical placement of the polysilicon. So, what I am going to do is I am going to tilt it 90 degrees. So, just choose it, go to edit, the rotate 90 degree, yes. So, this is my PMOS, and I need to adjust the length and width. So, double click on this, PMOS width is, so PMOS width is 20, length is 2, I am going to say it okay, and then I am going to get the, before getting the NMOS, let us try to work on building the proper PMOS. So, this is my polysilicon. Again, if the it is too much zoomed in, you can always use control 9, control 0 options, as I have told in the previous lab. Fine. So, the red color line is your polysilicon, and this is your source and drain. Now, what exactly, when we look into the cross sectional view of the MOSFET, how exactly the MOSFET is structured? As I was showing, the middle portion is your polysilicon. Just imagine you are viewing from the top view, and this is your N plus, and sorry, if I am using it as a PMOS, then this will be P plus, and this also will be P plus. So, on beside the polysilicon you will be having P plus diffusions. So, here also I need to add P plus diffusions, since I am going to construct PMOS completely. So, that P plus diffusion here is nothing but your P active region. Place it over here. Fine. If it is showing some error, that is fine, because these are some errors which we call it as a the lambda based design rules, and one of the few rule which says that the minimum distance rule, and then possibly the distance is not optimum. So, it is going to throw some error, we are going to rectify that soon. So, this is the P active, and place the same P active on the other side as well. Now, try to map the lengths of this P active regions. So, X is your horizontal, Y is your vertical. So, make it as 20. So, yes, it has now equal length as of your polysilicon. So, again you make it as 20. Now, left click over here. Now, what was the thing that we are supposed to do, since this is P plus active region, this is P plus active region, and both are connected through the channel and they are tied to the gate. So, I need to have an interconnection between these two. So, left click over here, come down and right click. When you do this, try to see that this should be marked in the green color. If it is coming in the blue color, which means there is a creation of a metal. So, in that scenario, immediately remove all these things and try to construct the things right from the beginning, and always try to save the work as soon as you do some modifications on your tool. And similarly, I will just left click, come over here, right click, there it is. Now, as you can see, they are placed very distant apart. So, what I am going to do is I am going to select this, and I am going to use the keypad arrow keys, and I am going to bring them close enough. Just look how much close I am going to bring. I am going to bring close enough such that this horizontal patch is not visible. Yes. So, bring in such a close so that this horizontal patch is not visible. And the moment you do it, go here, go to DRC and say check hierarchically. And like I was telling in the last class, this hierarchical checking will let you know if there are any sort of errors. So, if I have this kind of distant and if I do this, there is an error. And what is that error? You can always find it in the Explorer, which is placed over here, and it says there is a creation of a notch. If I double click, it says. So, always try to see to that there is an ample, you should not leave any distance over here, and then keep running the DRCs, 0 errors. So, now PMOS is done. Now, what exactly we did in the schematic? Once a PMOS is being placed, we set the model. Now, similarly here also we are supposed to set the model. So, click on this, go to tool, simulation, set spice model, and there is spice model is hidden over here. And how do I extract it? The one easy way is to zoom in and then extract it and then again zoom out, or what I can do is you click over here, outside somewhere over here, press the control button, go on the on this PMOS, or else what I can do, I will just zoom in, keep pressing the control button, keep clicking this particular body. See, if I keep clicking here, the moment you get a cross section with a white patch on the spice tool, leave this control and drag it. So, what I am doing here, click somewhere else outside, holding the control button, keep clicking this. The moment you feel a white patch has been checked on the spice model, leave the control button, drag it outside, and then control I to edit the text and name it as PMOS. So, since the same step is being adopted what we have done in the layout. Okay. Now, the set spice model has been done. Fine. Now, this PMOS is being created. Now, on a similar line, let us try to create the NMOS also. Now, to create the NMOS, so there is an NMOS component is there, place it over here, it is horizontally placed in the polysilicon, tilt it and double click on it, change the width from 3 to 20, apply. The same length and width that what we have used in the schematic, and then since this is an NMOS, I should be having N active region on the either side, place it and adjust the length. This will be 10 and this will be y axis will be 10, and again left click, come over here, right click, and there is a creation of a green patch, which means there is a connection. Left click, come over here, right click, and try to adjust the synchronicity using the arrow keys and try to push this close enough such that this horizontal connection is not visible. And once you do that, try to run the DRCs, and you can just check over here if there are any DRCs errors are coming, no errors. So, which means my NMOS is also ready, and try to have some distant apart over here. So, for that I am going to select it and bring it little bit down, because I am going to give the input also over here. So, again go to tool, set spice model for this also, control I, NMOS, done. So, now your this entire structure is done. So, I need to be joining this polysilicon. So, here is my polysilicon, left click, come down over here, right click, this entire red patch has been created now, and this is your V, which is over here, and this will be your output which you are going to join over here. So, the same way how you have drawn the stick diagram, and the same way you are going to join it. So, this portion and this portion will be joined, and joining will happen with the help of a metal which is shown in the blue patch, and this is connected to VDD. And when we connect the VDD, this one more thing was connected over here, and that is nothing but come down over here, and as you can see over here, when we have the MOSFET, if I have a PMOS, and what this will be always based on the N substrate or N well. So, which means all these are connected to the N substrate. So, in order to have the connections in a proper manner, I should also have the N substrate or N well. So, what I am going to do is I have the N well, since I am dealing with the PMOS, so it will be N well. So, I am going to place that N well over here, and again double click on this and adjust the width. Now, Y size, I will just double click and keep the Y size somewhere to 12, let's do that. What is y size? Yeah, sorry, it should be x size. I'll make it 15. Let's see, it's still having not the, it is having mismatched size, so I'll make it as somewhere around 22. Yeah, it's quite okay. And this is for PMOS, I have kept it as N well, and for NMOS I'll be keeping a P well, because for NMOS there will be always P substrate, so that means P well. So there's a P well over here, bring it over here, place it, double click, X size. Yeah, now what was the thing, this portion was connected to VDD and this portion was connected to ground. The same thing, this portion is now connected to VDD. Left click over here, come down, right click, left click over here, come down, right click. And once you do this, try to join and bring this close enough so that, because they are not different entity, so just this, these black spotted marker joints together, and keep doing the DRC. Now there are 4 DRCs, let me try to rectify them. Yeah, what is that? A minimum width or height error, N well less than 12 wide. So this is not the width that I was expected, so let me make it as 25, and again let me make it as 25. Again this width depends on the way how you have joined over here. Let's run DRC once again. Oops, there are 5 errors. Let's try to check before getting into this. Let's try to do this. Yeah, so notch error indicates this have close, very close connections possibly. Keep running the DRCs, keep doing the DRCs until they get rectified. I'm going to do once again DRC. Yeah, there are only 2 errors, minimum width or height error. So let me make it to 23 once again, save it, and there's only 1 error, possibly it will be this thing, save it. Yes, now there are no errors and no warnings. Perfect. Now everything is done. Now you are supposed to give the inputs and outputs. Now as we know that the input is on the polysilicon only, so which means I will be giving the input over here. Just left click, extract the polysilicon, and that will be your input. And how do you give the input? By creating the exports. Control E, that is your in, is input. Okay, extract, left click, right click over here, Control E, out, characteristics is output, and this is Control E, VDD, it's power, Control E, GND, ground, all set. Now your entire layout is done. Now the main thing that you are supposed to do is run the transient analysis as well as the DC analysis. So I'm going to copy paste the same DC analysis as well as transient analysis, whatever we have done for our previous schematics. So where is my inverter? Yeah. So I'm going to place the same this thing spice code. So I'm going to name it as V1, V2 ground. This is V3, and what is your input? You have named it as include. I'm dot include, and you're going to perform the transient analysis. This is run the analysis for 100 nanosecond with a resolution of 200 picosecond. And this everything we have discussed already, and say OK, save it, go to tool, spice simulation, write spice deck. Let's wait, it is going to open up. You ignore all these things and remove all the things that are above this dot page option, save it, run it. Okay, Just remove this, include none also, and since I am doing the transient analysis, I require 2 plots. I want to drag it, add a trace, input, add a trace, output. Oops. Now possibly the reason of getting this kind of output is, let me check over here in the spice code, there is, yes, as you can see in the spice code there is a no space was given over here. Yes. Now if I run it, so remove all the things that are over here, include none also, remove it, save it, run it, add plot panes, add a trace, input, add a trace, perfect. So this is how the inverted output comes even in the layout also. And the main advantage of getting the layout is, here there are 3 aspects that I can see, or 3 capacitances that are extracted over here. So when we perform the layout, we can see different parasitic capacitances that are created when we perform the layout, and that is why we convert the schematic into layout, and we are inching even closer towards the actual physical reality of the inverter. Now this is a layout which we send, if we send it to the fabrication center, they can fabricate this entire the inverter and gets and we can get a physical actual layout. So that is the reason of doing this the layout. So this layout is again going to help us in giving lot of aspects. We have seen the waveforms, now it is also going to give us parasitic capacitance. These are the different parasitic capacitance in terms of femtofarad. And like I was telling, this is your, if I am talking about NMOS, this is source, gate, drain, and again this is body. And what about these? This is the length of the NMOS, width of the NMOS, and AS stands for area of the source, 4.5 picometer, area of drain, perimeter of the source, perimeter of the drain with respect to NMOS. For PMOS, again the same things. So all these aspects can be found out in the layout kind of thing. Now let me try to run the same layout and perform some DC analysis, and let me take the example of, let me run the layout which we have drawn over here, yes, and let me write the spice code with respect to DC analysis, V1, V in. Yeah. Now one thing you should remember here, the dot DC analysis when we draw over here, here the value what you are going to write, it is not the value you are going to write with respect to the in what you have mentioned over here. You are going to mention that term which you have given prior to in, that is V3. So if I write in over here, you are going to get the error. So try to mention V3 over here, and this indicates perform the DC analysis from 0 to 5 volt in a step of 1 millivolt. So if I perform this now, spice deck, and run it, it is the same. Now here I do not require 2 plots, I require input. Input is rising from 0 to 5 volt in a step of 1 millivolt, and output is shown like this. So this is exactly your Q point analysis that we have done in the theoretical subject, and this is going to give us the value of Q point, the operating point of my inverter, how it is going to have the intersection with respect to input, and this is the point where both the MOSFETs will be in the saturation region, and we are going to get the optimum value of the output when we operate at this particular point. And as and when I keep on changing the width and length of the MOSFETs, of course length I cannot change. If I change the width of the NMOS, let us say 6, and if I just run it, you can just see the change in the waveform, it is shifting over here, right. And again if I change the width of the PMOS, again there will be change. So I can have the shifting of this curve either to the right side of the operating point which we obtained in the first case, or to the left side of the operating point which we obtained just now, and the moment of these operating point or the curve, we call it as a skewing of the MOSFET. So, this is a high skewed MOSFET. If I get the waveform here, it is low skewed MOSFET. So, basically it is going to give us the relevance of the operating point, at what particular voltage I am supposed to operate. So, this is what the information I am going to get from the layout perspective when I perform the layout operation. So, we saw both the transient as well as DC analysis in this particular lab.